Hello again. So our first speaker of the second session is Omri, and he's going to talk about sublinear algorithms, large networks via core-periphery decomposition.
Yeah, so this is joint work with several co-authors. I would like to highlight some of the excellent students who worked on this project. So Nadia is here. Sabia is around the workshop. I don't think he's here right now, but you will see him around. And Tim is an undergrad student at ETH that we worked with together when he visited MIT. The project, the couple of papers that I'm going to show here do not include Tim. He's a recent joinee, but we have more to come. So, sorry.
It's hard to hear you. Can you just speak up?
Yes. Okay, so this talk is about implementing algorithms for large, real-world, mostly social networks with insights from the sublinear world. So we are going to implement sublinear algorithms, or algorithms that take some sublinear aspects from in real-world social networks. And before we start with presenting you the algorithms and the data structure that we constructed in order to solve these tasks, I want to tell you about a few structural properties of large real-world networks. So, I mean, clearly these are not worst-case graphs. They look very different than so the type of challenges that we have are typically very different than what we see in the worst-case regime. So the first relatively well-known property of large networks is that the degree distribution that they have satisfies at least approximately a power law. So by power law, I mean that the fraction of vertices that have degree d scales something that is like so degrades polynomially with d. And so, for example, if you look at the log-log scale of graph, you're going to expect the number of vertices per degree. You're going to you expect to see something that looks like a straight decreasing line. So for Twitter, this is how it looks like. So it's kind of more it's kind of more static at the highest degrees, but after you look at the highest degree vertices, the most followed users, it does look like kind of a decreasing line, a decreasing straight line. And obviously, I mean, in power law graphs, the highest degree vertices are very high degree. So Twitter is, or now it's called X. So X is a good example of it. The highest degree vertices nowadays have more than 100 million followers. Some of them organically, some of them maybe not, but they have lots of neighbors, lots of followers if you think about a directed graph. Yeah, the most interesting theoretical regime for Paolo is when the exponent is between 2 and 3, because it turns out this way, but one reason is that the expected degree in this case is finite, but the variance is infinite. Okay, so many types of complex graphs have parallel degree distribution. This is one structural property that they have. Another structural property that they have is what is called a core-periphery structure. So you might expect that when we have graphs that have such a high degree vertices, you might expect that the high degree vertices will be well connected among themselves and perhaps, and of course also to the rest of the graph. And then the lower degree vertices might be like more isolated, might be more like peripheral. So this is not guaranteed just from the degrees, but we would expect it if it's not like a worst case graph with this degree distribution, we would expect that to have this kind of structure. So these are a few examples of large, and even not so large. So this is a relatively small graph, but this is a few examples of real world graphs. You see that we have some clusters in the middle that are very well connected to each other, and periphery vertices that are connected to one or a few vertices in the middle. And another interesting property that this is, I think, more specific to social networks and to information networks than perhaps to other types of networks. So another interesting property that they have is that if you look at the core, if you look at the higher degree vertices by some measure, it turns out that they have a domination number that is very small. So almost all of the vertices that are sufficiently engaged in the network. So here, this is some graph that we plotted early on in the research, in our research, where we didn't know what core-periphery is. So we use as a proxy all nodes that have out degree in the network that is at least 10 as what we thought of as core nodes. So when we looked at these nodes, and we looked, for example, at the 0.1%, so 0.001 fraction of the highest degree nodes in the network, so almost all nodes that have out degree at least 10 have a neighbor that is very high degree. So the the topmost highest degree nodes in the network dominate almost all nodes that have sufficient engagement in the network. And this becomes more pronounced for a larger graph. So the two largest examples that we looked at were Tumblr. It's a social network. So this is actually the full network of Tumblr, and Twitter MPI, so some snapshot from Twitter that is a bit older. And in these two examples, we see that this sublinear almost domination phenomenon is strongest. Okay, so we have quite a few relatively strong properties of graphs, and we would like to use them somehow. The spoiler is that we are going to work with some explicit decomposition of the graph into some sublinearly sized core of the core. This is, we call it L0, and it is going to induce the decomposition of the network into several layers. And we're going to implement sublinear algorithms using this decomposition. Yeah, any questions so far? All right. So I'm going to talk about two tasks where we could use this kind of structure to implement efficient algorithms. So the first task that I would like to speak about is that of sampling multiple nodes. So basically, we start at a single, let's say, random node, and the goal is to reach many random, ideally uniform, ideally independent from each other points in the network. So we start at a single random node, and the query model that we explore, we work with a sublinear query model. The query model that we work with is one that allows query access, one that reveals the neighbors of the vertex that we query. So it's not just a single edge query. We actually, given the name of a vertex, we see the names of all the neighbors of this vertex. So this is another query. And the goal formally is to generate a k-tuple of vertices that is almost uniform among k-tuples. So we want the probability of any k-tuple to be picked to be at most 1 plus epsilon more than what we would get if we sampled k-tuples uniformly. It's one-sided, by the way. So in this definition of the problem, there could be k-tuples that are much less likely to be picked, but no k-tuple is very likely to be picked. Right. okay, why study this problem? So many algorithms in data mining and in graph mining assume access to random nodes. I think the most well-known of them is PageRank. And this kind of problem is also a proxy for kind of trying to understand how we can explore as many different kind of parts of the network as possible with as little queries as possible. And also, so I told you that the query model is that given a vertex, I get the list of all of its neighbors. So as theoreticians, it might look unrealistic for us, but if you look at the API, for example, of X, and this was retrieved just yesterday, you will see, so I think the text here is too small, but it says that this, for example, API call returns the list of users who are followers of the specified user ID. And if you use the API of X, you are only allowed 15 requests per 15 minutes. So it's rate-bounded queries. We really have small amount of queries in order to understand what is going on in the graph. So this is actually realistic, this specific query model. All right, so back to our problem. We want to sample multiple nodes in our graph, and we assume these characteristics of large networks, parallel degree distribution, core-periphery structure, and so on. So I guess the first, and I didn't write it here, but the first and obvious algorithm that one could try is just to do a BFS over the whole graph, but then this would have a linear query complexity. This is not good enough for us. But the first reasonable algorithm that one can actually think about is a random walk. So for example, you take a uniform random walk or a lazy random walk, and you do some rejection sampling because some vertices, vertices that are higher degree are more likely to be visited, so we need to do some rejection. So if you do this kind of process, sampling a single node will take you something like the average degree of the graph, which let's maybe assume that it is pretty small, times the mixing time of the graph. But mixing time is sometimes not that small, so we'll see some numbers soon. And this is essentially optimal. So there exist graphs for which this multiplicative dependence in both the average degree and the mixing time is required. And as I said, there's an issue with this. So the mixing time is, we do think of like the mixing time of social networks as being perhaps not that bad. It's not like in worst case graphs, but it's not logarithmic as in expanders, for example. So in applied works that try to measure the mixing time of actual real world social networks, they found out it takes up to several hundreds and even a couple thousands for walks to converge. If you want to now, so if we go back to our task, which is sampling multiple nodes in the graph, perhaps spending the mixing time each time is not ideal. So the question is whether we can somehow bypass this mixing time dependence. Okay, but now let's go back to the structural properties that we know about social networks. So we know that we have a core-periphery structure. And if we think for a moment about the extreme case where the core is just, for example, a click, and then the periphery, let's say that is just a bunch of isolated nodes, it turns out that if we knew that it was a click plus just isolated nodes, we would be able to sample uniform nodes from this kind of graph in O of 1 per node sample. So obviously, in idealized kind of structures that look like core-periphery networks, we can do things that are very different, and we don't have things like, okay, in the example that I just mentioned, the mixing time is relatively small, but the point is that we can use the algorithms that look quite different than what we saw with random walks. Okay, but I'm going to present an algorithm that looks a little bit like this. So it uses an explicit decomposition of the graph that we construct in the beginning, and then using this decomposition, we are going to try to reach the difficult parts of the network more explicitly. Okay, so the algorithm that we propose, it's called the sampler. This is with Talia, Joel, and Dimitris. It basically starts by decomposing the network into an explicit core-periphery decomposition, where L0 is the core of the core, or the dominating set of the core. So I mentioned in the beginning that the higher degree nodes in the network tend to have a sublinearly sized set that dominates them. So let's take this set, call it L0. And then L1 are the neighbors of L0. And what we postulate is that if all goes well, L2 is going to break down into small components. So it's going to be like a very small size components. And then, okay, so we'll get into it, but sampling will basically involve trying to get into these small components. Right. So the first phase of the preprocessing is trying to build the core greedily. And here, so in this bounded query model, where we can only, so again, the query model allows us to see the names of all the neighbors of a node that we choose. So basically what we do is we try to greedily collect nodes that we perceive as the highest degree. So for example, if we start with this node on the left, so it sees several neighbors, and then we query one of its neighbors arbitrarily. So these two queried nodes that we have so far have some joint neighbor, so its perceived degree is 2. All the others have a perceived degree of 1. So we query this neighbor, and we continue until we complete the construction of L0. So of course, in worst case graphs, this is not going to work. Hence, this is a heuristic. But it turns out that in the networks that we tried, this actually was able to collect almost all of the very high degree nodes in the network. So it did collect a good proxy of what we saw is a dominating set in the beginning. All right, and with this L0, so all of these nodes that we collect and query, we call this set L0. So with this L0, we have basically a decomposition of the rest of the network. So L1 will consist of all the neighbors, the direct neighbors of the nodes in L0. And then L2, or L at least 2, this means nodes that are distant at least 2 from this core of the core. This will be the rest of the network. And what is cool about it, and again, this is connected to the sublinear almost domination, is that even sublinearly sized L0 will already decompose L2, so the periphery, into tiny components. So for example, in a graph, in graphs with millions of vertices, so for example, in a graph with 60 million vertices, we observed that you only need tens of thousands of vertices in L0 in order for the average, it's some sort of weighted average that was relevant for our algorithm, but the average size of components that we have in L2 is going to be less than 10, so less than a constant. So this is basically, so this key observation, this is basically the key for our algorithms to work well. You have to have L0 so that the non-neighbors of L0 are going to be tiny components, are going to decompose into tiny components. And now, for example, if we want to do sampling, so the idea is to, we start from L0. These are nodes that we already queried, so we know all of their neighbors. And we try to explicitly, I mean, okay, if sampling from L0 and L1 is easy, but sampling for the periphery, which is the difficult task, is done by explicitly actually trying to reach the periphery. So we try to reach from L0, we try to go to L1, and from L1 we try to go into edges that go into the periphery to L2, and then we need to do some rejection, same as we do with random walks. So basically, we have, for each component, we have some probability for it to be reached, so we need to reject by this probability. And it turns out that this is much better than doing just vanilla random walks. On the left, we see the query model that I talked with you, that I mentioned to you so far. So this red line is our algorithm sample layer, and compare it to a couple other random walk-based methods. So you see that the number of queries per sample becomes as little as 5 after you make a few percentage points of samples of nodes, whereas for random walks it's something like maybe 10 times more, something in this area. And these results on the right are for a stronger query model, where instead of just getting the list of neighbors of a node, we get the list of neighbors and also their degrees. So in this model, we also beat the relevant random walk quite handily. And there are some additional results for other types of networks. It seems to be consistent. So it seems that if you want to sample nodes in a network, it's better to start by, and you need to sample a large number of nodes. It's better to start by decomposing the network explicitly into this hierarchical core-periphery structure that we have, and then to try to explicitly go for the periphery rather than try just vanilla random walks. Okay, so this is the first instance where the core-periphery decomposition that we maintain helped for algorithmic purposes. Are there any questions about it? Yeah.
So how long does it cost? How expensive is it to compute this decomposition?
So it's very greedy and simple. I mean, so in terms of, okay, so we try to optimize queries here. In terms of running time, it's going to be linear in the number of edges that we see. So linear in the size of the graph in general.
Does it have any relation to K-cores, like core decomposition?
To which core decomposition?
Standard core decomposition, like arboristic and degeneracy gives you K-core decomposition.
Yeah. So right. So K-core is a formal way to define a core. I guess what I call by a core is kind of more vague. I mean, it's not like well defined mathematically, but it means like a set of nodes that are well connected, more expanding maybe, have some better centrality properties. So
like have you compared this decomposition with K-core decomposition and observed that they're similar or not?
I mean, okay, so we needed the sublinearity. We needed to identify a set of nodes that is sublinear and use this in order to run our algorithm. If you look at the K-core of a graph, if you look at let's say the 3 core of a graph, it's probably going to be linear in size. So it's probably going to include both L0 and L1 in our case, or at least large parts of it. So yeah, so we need the sublinearity. The K-core is not going to give this. All right. So the second application that I want to present is about computing distances. So the basic task is given an undirected graph G to build a data structure that supports shortest path queries. Well, maybe approximate shortest. Maybe we allow some additive error of 1 or 2. We prefer not to, of course, but let's say that we allow a little bit of additive error. And yeah, and the pairs are unknown in advance. So we want to build a data structure that, upon given a query, we will be able to compute the shortest path query relatively quickly. In some cases, you don't need the shortest passes. Sometimes you only need the distances. But this is well motivated. I mean, a lot of centrality estimation measures in social networks rely on distances and sometimes on passes between vertices. Measuring distances is essential for many graph learning purposes and so on. So measuring distances and finding shortest paths is a relatively basic task in data mining. And we would like to support, to build a data structure that supports shortest paths and so also distance queries that are approximately optimal. All right. So if, let's say that we want to just support a single query. Let's start with this. The first solution that we can come up with, again, is a BFS. We can just start running a BFS from S and hope we find T at some point. But this is going to be linear in time. This is going to, we're going to need to go over all the edges. So this is not really scalable when you want to make many queries, even one query actually. But in the single query case, one pretty good solution is to do a bidirectional BFS. So one pretty cool fact is that if instead of running a BFS just from S and trying to find the other endpoint T, you start a BFS from both S and T, it turns out that these BFSs together will typically need to cover much less than the entire graph. So if we run this on a random Erdős-Renyi graph or some other types of random graphs, or actually it's already known that even for general expanders, if you run a bidirectional BFS, the amount of edges that you need to see is sublinear in the size of the graph. So if you think about Erdős-Renyi graphs, if you let's say with constant average degree. So if you try square root n edges from this side and then square root n edges from this side, with constant probability they're going to meet. Unfortunately, so this is good for if you want to compute just a single query between 2 points in the graph. Unfortunately, there is a polynomial lower bound, so it is sublinear. It's a polynomial that is less than n, but it is going to be a polynomial, n to the omega of 1, at least as long as we don't run some preprocessing. And this is in theory, and in practice, it doesn't scale very well. We will see some numbers. But yeah, it's not really a practical solution if you want to run, I don't know, millions of queries on a large graph. It's good if you want to run a small number of queries. Okay, so this was case one where we want just a single query and we don't really want to pay for preprocessing. Second case is which is more useful practically, so it's in more. So the line of work is a bit more extensive. Is the case where you want to support a very large number of queries, and you are willing to pay for preprocessing that is relatively expensive. So there's a long line of work on landmark-based solutions that basically pre-compute distances between vertices of the graph and some set of landmarks. And they use an idea called two-hop labeling that basically, so for each vertex, you maintain a set of labels that are connected to it in some way. And for any two vertices, the shortest path between these two, so the distance between these two vertices can be computed by intersecting the sets of these landmarks. So this allows for very fast query answering. So in practice, it could be up to milliseconds, and in many cases much less, even for large graphs. But the preprocessing is very costly. So if, for example, the set of landmarks is the set of all vertices in the graph, the space complexity could be quadratic in the worst case. But and it's not just a theoretical issue; it's also difficult to scale in practice. So it tends to work for graphs up to maybe a few millions of vertices, but above that, you need a lot of implementation tricks, and it sometimes doesn't work very well. So naturally, we want some solutions that have good query time, that are able to support millions of queries, but also have some scalable preprocessing capabilities. Okay, so our core-periphery decomposition, the same one as before, comes to the rescue. And the idea here is to construct basically the same type of hierarchical core decomposition. And now when we want to find a path between some S and T, we basically try to run a BiBFS. Well, we know that it is an algorithm that works well, but at least for a single query. So we try to run a BiBFS from S and T, but we truncate it if we don't find it relatively quickly. So either the BiBFS between S and T meets, or both of the trees reach L0. And in this case, we kind of take the highway. We try to go through L0. So the examples on the left so the example on the left is one where the trees meet before they enter L0. And the example on the right is one where the trees reach L0 before they meet, and they actually find the actual shortest path. But this method is not exact anymore. So the example in the middle shows a case where the trees reach L0 before they meet each other. And this causes the path that the algorithm outputs to be worse than the actual shortest path. So this is not exact anymore, unlike the existing solutions that I mentioned so far. But it's not too bad. I mean, the additive error is pretty negligible in many cases. So we ran some experiments on graphs up to a few billions of edges. So the largest one is 1.5 billion. And what we see is that, and we have several variants of our algorithm. How much time do we have? Okay, yeah, I'm pretty close. Okay, so we ran several variants of our algorithm that do some more or less pruning when entering L0. And it turns out that we are able, with this method, to achieve query time that is competitive with landmark label with landmark-based methods. So, for example, it's the leftmost column in this graph. So, on the small graphs where the landmark-based solutions, the ones with the heavy preprocessing, were able to actually complete the preprocessing, and so we were able to compare with them. The running time is relatively similar. This is for our most efficient methods that do the highest amount of pruning. Whereas for the 5 largest graphs, these landmark-based methods just did not finish, and our methods did finish, but can't compare. But for the space cost, we see that we see a reason why these landmark-based methods did not finish. So the space that they need for the indexes is at least an order of magnitude more than the size of the graph, whereas we use amount of space that is less than the amount of space used to just store the graph itself. And I mean, well, it seems that it seems unfair. I mean, it seems that we beat the space requirements quite handily, and also have the same query time. So we need to pay somewhere, and we pay with an additive error. But the additive error is actually not that bad. So in many, so for example, in the largest graph that we observe, most of so in the method that do less pruning, so we almost always output the correct shortest path. And in the method that does more pruning, we almost always output a path that is, so more than 99% of the times, we output a path that is the shortest 1 + 1. So almost shortest path. We also have some theoretical result that is, I'll skip it quickly. So yeah, so we can, on random power law graphs, the Chang-Lu model, we're able to get a preprocessing that is sublinear in terms of number of queries, and the per query runtime is actually n to the little of 1. So for by BFS, we saw that it's n to the omega of 1. And an additive error that is much less than the diameter of the graph. So the diameter is logarithmic. In our case, the additive error is log-log. And could be lower. I mean, it's not clear that our analysis is tight. Okay, let me summarize. We saw 2 applications of this hierarchical core decomposition in practice. And there are more applications to come. It seems that this kind of like explicit way to look at large graphs is very useful. And in fact, it looks a little bit similar to work that people did in transportation networks, in road networks. And one cool notion from that literature is that of highway dimension. So basically, if you take 2 points and one of the points is not within like a small ball around the other, so low highway dimension means that they are going to go into so like any path between them is going to go through some highway, any shortest path at least. It seems interesting that that social networks also have some sort of highways, like road networks, and also the theoretical foundations that we have are relatively weak. So there's a lot of work that needs to be done in that front. And I would like to conclude with a statement that it seems that this kind of structures could be useful for applications in distributed settings. So, for example, we can use these kind of highways to get good measures for distances between far away vertices, and we might want to be more accurate. We might want a more accurate kind of local solutions. Okay, I'll finish here. Thank you.
You have time for a quick questions.
First question you already kind of addressed, which is there must be a connection to all the research that's been done on road networks. It would be interesting to explore that. And sort of a related question is, we've sort of got one level of decomposition. Does it make any sense to do a finer decomposition within the core, or is that overkill, or have you explored that? Because the highway dimension, it's generally more than just 2 levels, I think.
Right. So for the first task of sampling nodes, it was quite crucial to have just one level of the one core of core. Yeah, for distance computations, I don't see a reason why we should. I mean, you could very well be right. We need a finer decomposition.
The first application core is small enough that we just do a random sample.
It's yeah. I think the thing is that you basically need to go through the cut between the core and the periphery in the first. It's crucial to do that, and for this you need a very specific structure, and it's a difference. Yeah, the type of structure that you need for this in computations is different, and it's because you go up rather than down.
Are there any other applications besides the 2 you mentioned?
Working on it. I'm not sure I should mention too much. Yeah, it seems very useful for many types of algorithms. Yeah. So for example, okay, maybe one example I can mention is that we do node sampling, and it seems that you can do subgraph sampling for larger subgraphs. If you want to do edge or triangle sampling, it seems likely that you can do it very efficiently, and we have some preliminary results.
Any other questions? Hey, let's thank Omri again.